Welcome pre-calc students. This is Mrs. Fallon. I am actually starting with a unit on trigonometric functions. So you should have your notes that follow along with this video. So feel free to go ahead if you haven't printed those off or if you didn't grab one while we were in class. You can always just take out some paper and kind of follow along with us. All right, let's go ahead and get started. So this first unit in pre-calc, if you probably already noticed, we have a lot of review. This is a trig unit. So there's a lot of conversation that's going to be happening in class about, hey, you remember this from last year, that kind of thing. You did a trig unit in geometry and you did a trig unit in algebra 2. So this is a continuation. And so in mostly this unit, we're going to get into a couple new things, but we're going to try to remind you of all the wonderful things that you learned last year in trig, because we're going to kind of move on to analytic trig and some other stuff in the next couple units, and that we'll need to have this kind of this background information fresh in your mind. All right, so first and foremost, what we want to kind of start with is just kind of a definition of what is a radian. And so a radian, I'm just going to write down the definition and you guys can kind of follow along as well. So a radian, as if you remember, is a unit of measure. And more specifically, a radian is the number of radiuses, and that's how we're going to say it, the number of radiuses of turns. Okay, so let me make sure that makes sense to you. So for example, I'm going to draw a circle here. All right, so if we have a circle, and of course we have a center of our circle, and we have a radius, right? So this is a radius from the center of the circle out to the edge of the circle. So what a radian is the number of radiuses of turns. So for example, we know that a radian is the same unit of measure, the same length as one of these radii. And so obviously there are multiple radiuses in a circle, right? So it doesn't really matter which one you measure, but a radian is basically the same length as a radius. And so what we're looking at is, let's say this was 10 inches. And then if we kind of go around, how many radians would fit around our circle? But then let's say we did a tiny circle. I'm just going to grab another sheet of paper here just for a second. You don't really have to draw this, but let's say I did a small circle. And instead of saying, 10 inches, this is 2 inches. Well, what we want to get at is this length, okay? And we measure it around, and we measure it around, and we measure it around, and we measure it around. This length is going to be the same number of radiuses around as the bigger circle, even though this was, let's say, 10 inches, and this one is 2 inches. The same number of radiuses around our circle, so 1, let's say 2, if we kind of think about how many radiuses would fit around if we kind of just measured how long this is and just kind of went around our circle. And I didn't do that really perfectly, but you get the idea. So what I'm trying to get at is no matter what size circle you have, a radian relates to the length of the radius. So whether you have a teeny tiny circle or whether you have a giant circle, the number of radians is, since it's related to the length of the radius, the number of radians in a circle is the same whether it's a small circle, a large circle, or medium circle, because it has to do with the length of the radius. So obviously the bigger the circle, the longer the radius, and then the smaller the circle, the smaller the radius. But the same number of radiuses will fit around the circle as it will in a huge circle, as it will in a small circle. So that's what a radian is. It's a unit of measure. And so it's a unit of measure that measures basically the number of radiuses in a circle. And so we're going to relate this, and you might have learned this in geometry and maybe not. I'm not sure 100%. But let's say we remember this little piece of our circle. Okay, so I'm going to draw in another radius. So I can draw in as many radiuses as I want, or radii. So what we call this right here, this little piece, is we call that a sector. So a sector is kind of think of it as like a piece of pie or a piece of pizza. So it's like a fraction of the area of a circle. More importantly though, what we're looking at is, do you see this length right here? So that connects, so this piece that connects this to this, This is what we call arc length. And again, I'm not sure if you've learned that before. If not, that's what it is. It's the measure of kind of the part of the circle this sector makes. So let's say we know that this all the way around, this measures, you know, I don't know, 100 inches. Well, this piece right here might represent, you know, 15 inches or 20 inches or whatever. So this length right here is measured in units, like in meters or centimeters or something like that. It's the part of the circle that we're kind of used in this sector. So again, whatever unit of measure we're using, we tend to use to measure the arc length. I'm not really sure why we use S for arc length, but nonetheless, that's what it is. All right, and then we have this lovely thing called an angle, and we call it theta, which is that Greek letter. So in relationship, this angle is the ratio, which is just a fancy way of saying fraction, of the arc length over the length of the radius. So that was maybe a formula you learned in geometry, and again, I'm not sure 100%, but that is the formula for arc length. So how to find this measure to get this angle is related to this, you know, piece of the circle by taking this arc length, dividing it by this radius, and it will give you the measure of that angle. And so this measurement that we're measuring, like this angle, is measured in radians. So that unit of measure that we're finding here is the angle is measured in radians. There's really only two things that we measure angles in, right? So we measure them in degrees, we measure them in radians. So I'm going to write down here ratio of arc length, just so that you know what that means, because again, that S kind of stands, it seems a little strange, to radius. So that's what this angle measures. It's the ratio of the arc length to the radius. And again, what this measurement is in radians. We could ask you for the measurement in degrees, but you know, we'll get to that here in a second. All right, here's a couple examples just to kind of how we would use this. Suppose that you walk 10 meters along the arc of a circle with a radius of 5 meters. How many radians did you turn? Okay, so let's say here's a circle, right? And we're walking along 10 meters. So let's say we start here and we go here. So what I'm giving you here is the arc length. So this piece of the puzzle right here, we're walking along the arc of a circle. What that is your arc length. Obviously, it says a radius of 5 meters. So let's draw the circle. We'll say 5 meters here. How many radians, so we're finding an angle here, did you turn? So I'm going to go back up to this formula, which is our angle, which is our in radians, is equal to our arc length over our radius. So if we know our arc length is 10 meters and our radius is 5 meters, 10 divided by 5, we all know, is 2. Now remember, this is an angle, so this is not 2 meters, because technically the meters actually canceled out, right? Because the meters divided by meters. So what this is measured in is in radians. And the other thing I want to remind you of that you probably learned at some point when you did this in Algebra 2, radians have no units. So like if I was to measure this in degrees, I would put the degree symbol, or I guess the word degree after it. But if there's an angle and it just has a number, you assume that that means that it's in radians. All right, let's do another one. It says you walk along the arc of a circle with a diameter of 4 meters. So I gave you a little bit different information here. So I'm going to draw my circle. The diameter is 4 meters. But again, because we're looking at this formula up here, that arc length formula, we talked about the radius. So if the diameter is 4 miles, then the radius would be 2 miles. So you walk along the arc of a circle with a diameter of 4 miles until you have turned a total of 3.5 radians. All right, so again, the length of a radian we have to use the length of the radius. So if you kind of measured this, right, I'm just going to kind of eyeball it here, right? That might be 1, that might be 2, this might be 3.5. So we might be over here. Like if we're walking along, 3.5 radians might land me approximately right here. So that's kind of what we're asking for. So this is 3.5 radians. That's what that angle is measuring. And so what we're asking you to find is how many miles did you walk? So again, kind of different than in the last problem. This time we're asking you to find that arc length. So we're going to go ahead and take that arc length divided by radius. This time we know the angle. It was 3.5 radians. And then the arc length is what we're finding. And then the radius was 2 miles. So let's go ahead and solve this lovely example here. So we're going to go ahead and multiply both sides by 2. We are going to use those units since they don't cancel out. So we're going to multiply both sides by 2 miles. I get 7 miles is my arc length. All right, next we're going to talk about sketching some angles. So in Algebra 2, you probably also talked about something called quadrantals. So let me draw a circle, and we're actually going to draw something called the unit circle, which I'm sure that sounds familiar to you guys, hopefully. So I'm just going to draw in kind of my rough version of my unit circle. And I'm going to label for you my quadrants. So this is quadrant 1, 2, 3, and 4. Probably one of the only places we actually use Roman numerals. So what I want us to understand is, again, all circles are kind of the same, right? We talked about the number of radians in a circle. Whether it's a teeny tiny circle or a giant circle, they all have the same number of radians around. So you just take the radius and kind of measure. So if you go back up to this example here where we talked about 3.5 radians, when we measured it, it was like, you know, somewhere, if I would start here, it would be somewhere in quadrant 3 is where I landed. So, you know, and that's what I'm trying to get at, is the fact that we want to kind of measure how far or how many radians around is the whole circle. Like what I'm getting at is how many radians, like how many of these radiuses could fit in a whole circle. Well, 3.5 lands me here. What do you think lands me like right here in the middle? So you probably remember this a little bit from Algebra 2. You might remember that this would be a little more than 3. Well, what number is a little more than 3? If you're thinking pi, then you're on the right track. So for example, let's do the degrees first. So this is 0 degrees. We know this is 90 degrees. We know this is 180 degrees. And this is 270 degrees. And then if we go all the way back around again, we're at to 360, and then we can keep going around and around and around and around. But for radians, so if we start here, generally our initial side of an angle always starts on the x-axis. We have 0 radians. Remember, we have no units. If we go all the way around, like halfway around, I should say, we know that this is a little more than 3, or in other words, pi. That's where that pi comes into place. Pi is a number. It has really nothing to do with radians itself. It's just a number. It just happens to be on a circle. That halfway point happens to be, it always kind of equates out to that little more than 3. And so, you know, the mathematicians of the world created this value. They noticed that it kept appearing, and so we called it something. So we called it pi. Which means that if I went halfway around and got pi, that means all the way around would have to be 2 pi. And then you can fill in the rest, right? So like you would know that this would be a half pi, and this would be 1.5 pi, or in other words, 3 pi over 2. So when an angle falls on those 4 quadrants, like if it falls here, 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 we call that a quadrantal. And we'll get to that in a minute. But what we're going to talk about now is how to draw angles. So turn your paper over. And so I wanted to give you ones that says draw an angle in standard position and then convert from degrees to radians. So what I want us to understand is where is 1 radian? In what quadrant would 1 radian be? So if we know this is 0 radians, and this is pi radians, and this is pi over 2, and this is 3 pi over 2. And then this is 2 pi again. So approximately, if I started here and went all the way to here, that's pi. Well, that's approximately 3.14, right? All the way around, you might have heard of 2 pi being like 6.28. So where would 1 fall? Well, half a pi, what's half of 3.14? So if we did half of that, you know, is about 1.5 something, right? So that means this is 1.5 radians right here. So 1 radian would have to fall in quadrant 1. So if I'm going to draw an angle, I do my initial side, which is always on your axis, and then I find wherever I land at here. So this is going to be my angle measure. That's going to be 1 radian. And so it's going to land somewhere in, in quadrant 1. To convert from radians to degrees and degrees and radians. So if I'm going to go from radians, since that's what we're starting here, to degrees, you multiply by 180 over pi. And that has to do with the ratio of how many pi's there are in a circle. If you were going from degrees to radians, you do the exact opposite, which is pi multiplied by pi over 180. So let's do some conversions. If I have 1 radian and I'm going to want to get this into degrees, I am going to, put my little degree symbols here, multiply by 180 over pi. I'm going to throw that into my calculator, and I'm going to get 180 divided by pi. I get approximately 57.3. And we're talking about degrees. All right, let's do another one. So this one is asking for negative 440. Do you remember what happens when you have negative the angle measures? You go backwards that number of degrees. So we're in degrees here. You can see the little symbol. If I go backwards negative 440, so first and foremost, what I want you to remember is that 1 whole revolution around the circle is 360. So I went all the way around. So 360, I already went 360 degrees backwards. So I'm going counterclockwise. So I'm going backwards. And then I have to go another, 80 degrees, right? So another 80 degrees would land me, this would give me another 90. This would land me about right here. So my angle, notice that I did like the little squiggle to show that it's 1 complete revolution plus some, is going to land me in quadrant 4. So that's the angle I'm referring to. To convert from radians to degrees, I'm going to multiply by pi over 180. Notice that the degrees would cancel since one's on the numerator, one's on the denominator. Throw that into your calculator. You could reduce this and get, let's see here. You could get negative 22 pi over 7, and that would be an accurate answer, right? Like you don't have to write it as a decimal, but sometimes it's easier to think about the number of radians if you don't think of it in terms of pi. So it's up to you. I'm going to go ahead and write that as a decimal for you as well. So negative 7.7. So what that meant is I went backwards 7.7 radians. So remember, 2 pi or 6.28 is 1 whole, revolution, and then a little more would land me in quadrant 4. All right, let's take a look at this example. Identify the measure of the angle. So notice that this angle right here is that we're going backwards. So first and foremost, we know the angle is negative. Okay. I'm asking, so because I'm telling you this is pi over 3, I'm really kind of asking you for this measurement in radians. So pi over 3, there's no degree in it, there's no unit. And so what we can assume there, since there are no units, we know that has to be radians. So anyway, we're going to measure this in radians. So I'm going to go backwards one half of a circle, which we know is pi. And then so I went backwards pi, and then I went backwards pi over 3. So really what I'm doing is I'm taking pi, or negative pi, and I'm going to add negative pi over 3. And that would land me at this complete angle. So this angle would equal whatever negative pi plus negative pi over 3 would be. So you can think of it as a fraction, right? It has a denominator of 1. So I'm going to think of this as negative 3 pi over 3. So that's just negative 1. And I'm going to add to it negative pi over 3, which lands me at negative 4 pi over 3. Again, go ahead and leave your answer in terms of pi. A lot of times I will ask you to do that. You can also, again, write it as a decimal, but there's be a lot of cases in which we're going to leave it in terms of pi. All right, last but not least, this last example talks about, again, kind of thinking about where the angle ends up. So given the radian measure of an angle's rotation, determine the quadrant where the terminal side of the standard position angle sits. So we're looking at, this is what I'm giving you here are radian measures of an angle. So this is 1 radian, 2 radians, 4 radians, 7 radians. So again, we talked about 1 radian. We talked about this being pi, about 3.14. We talked about this being 2 pi, which is approximately 6.28. And this is 1.5 something, and this would be 4.6 something, right? So if I added 1.5 pi together. All right, so in 1 radian, we talked about would land me in quadrant 1. I should use Roman numerals here. So we talked about that one above. Radians would be more than 1/2 pi. Remember, this is 1/2 pi, and this is pi, but less than a full pi. So that would land me in quadrant 2. 4 radians. So again, we look at 6.28 is all the way around. This is 3.14 radians. 4 radians would land me anywhere in quadrant 3. And then 7 radians, knowing that a whole circle is about 2 pi, or is 2 pi, it's about 6.28, then 7 would land me back into 1, because I'd have to go 1 whole revolution plus a little bit more to get to 7 radians. All right, 37 pi over 4. So what I would like you to do in a situation like this, when it's not like a whole number radian and there's that pi involved, I like to think of it in terms of pi. So for example, 37/4. Remember back in elementary school where you had to take like improper fractions and make them into mixed numbers? So this is where that's going to come into play. So 4 goes into 37 9 times, because 4 times 9 is 36. And then since there's from 36 to 37, there's 1 left over. So all I'm going to do is I'm just going to rewrite 37 over 4 as 9 1/4. And of course pi. So now you could write this as a decimal, but I want to challenge you not to use your calculators. I want you to kind of beginning to think, to challenge yourselves not to use a calculator in this and to think in terms of pi. So 9 1/4 pies. Let's think about this. Well, how many pies are all the way around a circle? We know this is 1 pi, 2 pi. So this would be 4 pi. It'd be another revolution. So we go 1 revolution, 4 pi, 6 pi, 8 pi. 9 pi would be another like half, right? So we go, it's multiples of 2 here. This is 2 pi. So 2, 4, 6, 8. Then 9 1/4. Well, 9 1/2 would be here. So 9 1/4 would have to land me somewhere in there. And so all we're really asking is where would this angle end up? And so, there's obviously lots of like times around, revolutions around, but we're still going to end in quadrant 3. So I'd like to challenge you to think in terms of pi, so that way you're not always converting or needing a calculator to be able to do that. All right, that's it for now. We're going to go ahead and practice some of the skills. I would come to class with any questions, and we can kind of go over those before we get too far. All right, thanks.